Remember the definition of a Laplace transform for a function f of t. This is defined as improper integral of e to power negative st f of t dt. In previous lecture, we went over some basic functions, and let us list them here. First of all, the Laplace transformation of constant function 1 is 1 divided by s. The Laplace transformation of t to power n is n factorial divided by s to power n plus 1. The Laplace transformation of e to power at is 1 divided by s minus a. The Laplace transformation of sine of kt is k divided by s squared plus k squared. The Laplace transformation of cosine kt is s divided by s squared plus k squared. The Laplace transformation of hyperbolic sine kt is k divided by s squared minus k squared, and the Laplace transformation of hyperbolic cosine kt is s divided by s squared minus k squared. Remember the definition of hyperbolic sine of x. This is defined as e to the x minus e to power minus x divided by 2, and the hyperbolic cosine of x is defined as e to the x plus e to power minus x divided by 2. Just a quick reminder about hyperbolic sine and hyperbolic cosine. Now, since we have a transformation, we can find the inverse of these operations as well. Here we're going to introduce the inverse transformations. If f of s represents the Laplace transform of a function like f of t, it means that the Laplace of f of t is capital Fs. We then say f of t is the inverse Laplace transform of capital F of s. And we write f of t as the inverse Laplace of f of s. Let's take a look at some transformation and their inverse on the right-hand side. The Laplace transformation of 1 is 1 divided by s, so you can write down 1 as the inverse Laplace of 1 over s. The Laplace transformation of t is 1 divided by s squared, so t is equal to inverse Laplace of 1 over s squared. The Laplace transformation of e to power negative 3t is 1 divided by s plus t. So e to power negative 3t is the inverse Laplace of 1 divided by s plus 3. In general, if we have the Laplace transformation of basic functions, we can basically write their inverse Laplace as well. On the left-hand side, we write down some basic Laplace transformations, like Laplace of 1 is 1 over s, so you can easily write 1 as the inverse Laplace of 1 divided by s. The Laplace transformation of t to the n is n factorial divided by s to power n plus 1, so you can easily write t to the n as the inverse Laplace of n factorial divided by s to power n plus 1. The Laplace transformation of e to power at is 1 divided by s minus a. Equivalently, you can write down e to power at as the inverse Laplace of 1 divided by s minus a. The Laplace transformation of sine of kt is k divided by s squared plus k squared. Equivalently, sine of kt is nothing but inverse Laplace of k divided by s squared plus k squared. The Laplace transformation of cosine kt is s divided by s squared plus k squared. Equivalently, we can write cosine kt to be inverse Laplace of s divided by s squared plus k squared. The Laplace transform of hyperbolic sine kt is k divided by s squared minus k squared. Equivalently, we can write hyperbolic sine of kt to be the inverse Laplace of k divided by s squared minus k squared. And finally, since the Laplace transform of hyperbolic cosine kt is s divided by s squared minus k squared, equivalently, we can write hyperbolic cosine of kt to be inverse Laplace of s divided by s squared minus k squared. So let us take a look at some examples. This is what we list as the inverse transformation. For example, if I ask you to calculate the inverse Laplace of 1 divided by s squared, we're going to use b. We know that t to the n is the inverse Laplace of n factorial divided by s to power n plus 1. So inverse Laplace of n factorial divided by s squared, s to power n plus 1, can be written as n factorial. N factorial is just a number. You can take this number and write it outside your Laplace. And here, since we factor out, or we brought n factorial in front of inverse Laplace, you end up with 1 on the numerator. So how does this one is helpful to us? The inverse Laplace of 1 divided by s to power n plus 1 then can be written as t to the n divided by n factorial. So from the formula, you can derive another formula. Since t to the n is inverse Laplace of n factorial divided by s to power n plus 1, since n factorial is just a number and inverse Laplace is just a transformation, you can write n factorial in front of the inverse Laplace, and then you can divide both sides by n factorial, so you get t to the n divided by n factorial equals to inverse Laplace of 1 divided by s to power n plus 1. So all we need to do is to identify what n is. N plus 1 is equal to 5, so n is equal to 4. So this guy in turns is equal to t to power 4 divided by 4 factorial, which is 24. So far we saw the inverse transformations. Now suppose I ask you to find the inverse Laplace of 1 divided by s squared plus 7. So look at these formulas. Which one has s squared plus a number? On the denominator, I have s squared plus k squared for sine of kt. Also, I have s squared plus k squared, but on the numerator, I have a variable s. Here, I have k, which is number. So I prefer to use sine of kt, which is inverse Laplace of k divided by s squared plus k squared. So now I need to find k. K squared is equal to 7. So k is equal to square root of 7. Let's play around with this. Sine of kt divided by, remember that k is a number, so you can basically take this k and write it in front of your inverse Laplace as an operation, and then divide both sides by k. It's equal to inverse Laplace of 1 divided by s squared plus k squared. Very good. So now we can see the similarity. We have 1 on the numerator, we have s squared plus k squared on the denominator, and since k squared is equal to 7, k is square root of 7. Or you could simply write it this way. 1 divided by square root of 7 times the inverse Laplace of square root of 7 divided by square plus 7, which is nothing but 1 divided by square root of 7 times sine of square root of 7 times t. So from one formula, we can derive another formula. Guys, please note that you cannot write s in front of inverse Laplace because s is a variable, but k as a number can be written in front of your operation. Let's make it more interesting. Now I ask you to evaluate the inverse Laplace of negative 2s plus 6 divided by s squared plus 4. How do we solve this? We don't see any similarity between what we have inside the bracket and the popular formulas that we learned before. We're going to divide this fraction up into smaller portions. We're going to separate negative 2s divided by s squared plus 4 from 6 over s squared plus 4, so we can similarity between these two separations and these formulas that we learned. Now, since you have an operation, you can separate this into the addition of these two fractions and take negative 2 and write it in front of your inverse Laplace, and then take 6 and write it in front of your operation. For the first fraction, we have s divided by s squared plus 4. So you have s divided by s squared plus k squared. This is similar to cosine of kt. For the second one, you have 6 times inverse Laplace of 1 divided by s squared plus 4. On the numerator, you have to have k. Square root of 4 is 2. But in order to have 2 on the numerator, we have to divide by 2 as well. Using linearity and fixing up the constant, we can see that the very first inverse Laplace is negative 2 times cosine of 2t. And the second Laplace is 3 sine of 2t. In more interesting cases, we're going to apply other techniques that we learned in pre-calculus. For example, here I have s squared plus 6s plus 9 divided by s minus 1 times s minus 2 times s plus 4, and I want to find the inverse Laplace of this fraction. How do we do that? So if you take a look at the quantity inside the bracket, we're going to use partial fractions to break this off into simpler fractions. So our goal is to evaluate the inverse Laplace of s squared plus 6s plus 9 divided by the multiplication of these three distinct linear terms. We're going to use the method of partial fractions. As you remember, we're going to take this rational expression and set it equals to some simpler fractions. The very first fraction has unknown a divided by s minus 1, which is your very first linear term, plus the second partial fraction is going to be unknown b divided by s minus 2, the second quantity on the denominator. Finally, an unknown like c divided by s plus 4. So our goal is to find the values for a, b, and finally c. Let us begin. What are we going to do? We're going to take the common denominator between these three fractions and create a new fraction. We get a multiplied by s minus 2 times s plus 4 plus b multiplied by s minus 1 times s plus 4 plus c multiplied by s minus 1 times s minus 2, all divided by the least common denominator is the multiplication of these three distinct terms. Now, since the denominators are identical, the numerators must be the same as well. What are you going to do? You're going to take s squared plus 6s plus 9 and set it equals to this long numerator on the right-hand side. Then we're going to find the values for a, b, and c. So as you can see, the denominators are the same. So we don't have any issue with the denominators. The numerators must be the same. Very good. So far we saw that s squared plus 6s plus 9 is equal to a times s minus 2 times s plus 4 plus b times s minus 1 times s plus 4 plus c times s minus 1 times s minus 2. We can use a shortcut. The roots here are 2 -4, and 1. So if we set s equals to 1, s equals to 2, and s equals to -4, we can eliminate some of these terms and calculate the missing value. For example, when s is equal to 1, what do we have? You get rid of these two terms. So when s is equal to 1, you plug those into the right-hand side, and you end up with a times -1 plus 5. And on the right-hand side, if you do the calculation, you get 1 plus 6 plus 9, which gives you 16. So that's how you can calculate your a. With the same process, you can plug in 2 into the equation and calculate b, because these two terms now disappear. With the same process, if you set s equals to -4, you can calculate left-hand side, which is 1, and on the right-hand side, this quantity, and this quantity disappears, and you have your c on the other side. So a becomes 16 divided by -5, b is 25 divided by 6, and c is 1 divided by 30. What does it tell us? Remember that our goal is to find the value for a, b, and c, so we can break this fraction down into simpler fractions. We found a, b, and c. So our left-hand side is equal to -16 divided by 5 over s minus 1 plus 25 divided by 6 over s minus 2 plus 1 over 30 divided by s plus 4. Simply substitute a, b, and c here. Well, now you have s squared plus 6s plus 9 divided by s minus 1 times s minus 2 times s plus 4 as -16 divided by 5. Here we are taking the inverse Laplace of the quantity on the left-hand side. So you can basically write it this way. You get -16 over 5 of inverse Laplace of 1 divided by s minus 1 plus 25 over 6 inverse Laplace of 1 divided by s minus 2 plus 1 over 30 of inverse Laplace of 1 divided by s plus 4. Okay, remember how we defined e to power at. This is the inverse Laplace of 1 divided by s minus a. So the very first value becomes -16 over 5 e to power t plus 25 over 6 times e to power 2t plus 1 over 30 e to power -4t. So that's how we found the inverse Laplace of this rational expression.